Hello, my name is Steve Carlson. I'm a master's student with Robotic Workers Lab at the University of Nevada, Reno. Today, I'll be presenting our work on Towards Multi-Day Field Deployment Autonomy, a long-term self-sustainable micro-aerial vehicle robot. To unlock true long-term autonomy, aerial robotic systems have to be able to endure in the wild over prolonged periods of operation, which effectively means being capable of replenishing their power supplies without relying on human maintenance or any other stationary infrastructure. In this context, we present a novel aerial robotic self-sustainable autonomous system, which is capable of performing long-term or migratory operations in the wild through recurrent flying and landing to recharge cycles that can take place over the span of multiple days. In situ recharging is achieved using either ambient solar power or externally provided electrical power integrated on another robot, enabling the possibility for marsupial system of systems recurrent deployments. The core element that facilitates this is a custom-developed power management stack, which is an intelligent power harvesting and distribution board. It comprises a buck-boost converter and is capable of hibernating the entire aircraft by completely switching off all of the power-hungry high-level subsystems. For this project, we use the Mini-Hawk VTOL platform, which has been developed at the Robotic Workers Lab over the past 2 years. The newly developed components enabling this work are centered around the power management stack and its energy input paths, i.e. the solar array and the external contactors integrated on the landing skids. The power management stack core functions can be summarized as the input from either the solar array on the wings or from the external electrical contacts on the skids is ORed and input to the DC-DC converter. The DC-DC converter steps the voltage either up or down to approximately the same level as the battery, essentially power impedance matching. The battery management system performs cell balancing to equalize all the cells in the lithium battery. The aircraft electrical bus connections can be switched on or off using a set of load switches. The power management stack microcontroller communicates with the autopilot and the high-level computer, allowing for control and sequencing. And finally, we have various other peripherals that are articulated here. The system state machine consists of the following. The idle state occurs when the battery is fully charged, with the DC-DC converter inactive and the aircraft avionics fully powered on. If the battery level drops and the input source voltage is viable, the system begins charging by entering the init state. This state samples the input power source characteristics and IV curve, and then will either enter the maximum power point tracking mode or the constant current or constant voltage modes, with the former optimizing for power conversion efficiency, and the later for staying within the battery limits. If requested by the autopilot or the high-level computer, the power management system will enter the sleep state, completely disconnecting the avionics bus. While in the sleep state, the microcontroller also remains in a low-power sleep mode, and only wakes up intermittently to sample the solar input and to accumulate the elapsed time, such that it will resume aircraft operation by re-entering idle once the battery is recharged. Our power management stack is implemented as a set of 4-layer PCBs stacked in a double-deck configuration. The system uses an ARM Cortex M4 microcontroller. The battery voltage range supported is 12 to 28 volts. The DC-DC inductor is rated for 10 amps RMS for the MPPT charge path. The load switch can sustain 60 amps continuous and up to 160 amps burst. Auxiliary peripherals implemented include the lithium polymer battery balancer, an isolated UART interface for talking to the autopilot, and a flash memory logging mechanism. Power usage during hibernation is below 5 milliwatts. With this capacity at hand, we conducted a multi-day recurrent mission in the North Nevada region in mid-September 2022 during adverse atmospheric lucidity conditions due to a nearby active megafire. The GPS coordinates of the legs of the mission were pre-programmed, but the sequencing of recharging and hibernation phases were naturally handled by the power management stack. For safety reasons, the mission legs were designed such that direct line of sight and emergency control authority were preserved, and field testing crew with PPE and fire extinguishers were located at the takeoff and landing sites. The aircraft was strictly quarantined from any external physical intervention in order to demonstrate unassisted, self-sustainable deployment. The first leg occurred in the late afternoon, with the aircraft subsequently landing and hibernating overnight. The team also camped at the location overnight to ensure safety. The next morning, the aircraft resumed to full charge despite the challenging atmospheric conditions, and it took off to successfully perform the second leg, relocating to a hillside. The aircraft performed a second solar recharge cycle and flew back to camp in the third leg, ending the multi-day demonstration successfully. Finally, we demonstrated the system of systems marsupial external recharging behavior using a docking and recharging backpack developed for the Boston Dynamics spot-legged robot system. In short, this is designed for passive alignment and centering once the aircraft touches down, and comprises a set of articulated claws that grasp onto the aircraft skids and hold perfect retention against aggressive body movements during dynamic locomotion. While grasped, a pair of claws establish electrical contact, connecting a 12-volt external battery to the aircraft-mounted power management stack, which proceeds to perform fast recharging. Autonomous landings are accomplished using a transfer learning retrained version of the LOX Nano framework for the initial detection of spot, and the accompanying approach and descent, with fine positioning accomplished in the terminal phase using a fiducial marker on the docking and recharging backpack. We hope you enjoyed this presentation. Feel free to contact us if you wish to learn more.